The night sky, with its familiar constellations and ever-changing moon, is a comforting sight. For ages we've seen it as a symbol of things that last forever and stay the same. But that's actually not true. It's something we believe because of how we perceive time. In reality, the universe is a superactive place, constantly in motion and full of big changes. Every second, about 130 stars go supernova in the universe. Every second, several thousand stars are born. Billions of asteroids tumble through the void, and thousands of planet worlds are born in swirling clouds of gas and dust, all in just 1 second. So how can we keep track of all of it? How do we know where to point our telescopes at? This is the domain of time domain astronomy, the study of a universe in constant motion. Its practitioners are attempting to observe a cosmos in which the most dramatic scenes are often the most fleeting. The brilliant flash from two colliding neutron stars, for instance, can vanish from optical view within a matter of days. The very first light escaping from a dying star, a signal that contains secrets about the nature of the explosion, is brief. In this show, we dig deeper into the algorithms that let scientists sort through this ocean of change. Astronomers use such brokers to identify which signals to pursue in an endless stream of millions of alerts per night. How does it all work? Let's find out. To meet this challenge, astronomers have built a new generation of robotic eyes. On Palomar Mountain in California, the Zwicky Transient Facility, or ZTF, scans the entire northern sky every 2 nights. Its camera, with a field of view wide enough to capture a patch of sky larger than 100 full moons, operates more like a planetary scale security system. It takes an image of a section of the sky and compares it pixel by pixel to a reference image of that same section. Any object that has appeared, disappeared, or changed in brightness or position triggers an electronic alert. This automated process works with astonishing efficiency. The operation is fundamentally about spotting differences in a sequence of images. When it began operations, the facility issued a few 100,000 such alerts each night. Today, that number can exceed 1 million. And the flood is about to become a deluge. High in the Chilean Andes, the Vera C. Rubin Observatory has opened its eye on the universe in 2025. With its enormous 8.4-meter mirror and the largest digital camera ever constructed, Rubin will conduct a decade-long survey of the southern sky. Each night, it will generate around 10 million alerts and produce 20 terabytes of data. In its first year of operation, the observatory will gather more information than has been collected by all other optical telescopes in history combined. The sheer volume and velocity of this data stream make human review an impossibility. An alert is generated within minutes of an observation. If a person were to spend just a single second examining each of the million alerts from one night of ZTF observations, it would take more than 11 days to complete the task. Because celestial events could be so brief, an alert would be too late, the event would already be over. To really get a handle on these phenomena, everything from the first time we spot them to finally figuring out what they are needs to be totally automated. This becomes our classic needle in a haystack challenge. Astronomers came up with a pretty cool solution to this puzzle, something called an astronomical broker. Astronomical brokers are complex computer systems that sit between all the data pouring in from telescopes and scientists all over the world. Think of a broker like a global news service for the cosmos. It takes in millions of raw alerts, adds more context to each one, and then sends out personalized feeds to scientists who are interested in specific things. Upon receiving an alert, the system immediately begins by cross-referencing the alert's sky position with extensive astronomical catalogs. This initial step helps determine if the object is new or a known entity exhibiting unusual behavior. The core of the system is an array of machine learning algorithms. These algorithms are trained on vast data sets of known cosmic events, enabling them to recognize distinct patterns of light or light curves. For instance, they learn the characteristic brightening and fading of a supernova or the regular repeating dips in light from an eclipsing binary star. So by recognizing these unique signatures, the algorithms can classify new alerts in real time. Based on this classification, the broker sorts the alerts into dozens of different streams. A scientist studying exploding stars might subscribe to the likely supernova channel. A researcher hunting for asteroids near Earth receives a different feed. This allows individual teams to focus their attention on the small fraction of alerts relevant to their work. Several of these brokers now operate around the world, including LARCE based in Chile and FINC based in France. A broker can be programmed to listen to alerts from other kinds of observatories, such as those that detect gravitational waves or high-energy gamma rays. When an alert arrives from one of these facilities, the broker can instantly scan the millions of optical alerts from ZTF or Rubin, looking for a counterpart at the same position in the sky at the same time. When it finds a match, it creates a new data product, a multi-messenger candidate that is far more valuable than the sum of its parts. The broker becomes the intelligent hub where different streams of cosmic information converge to create new knowledge. The gains from this automated method have been remarkable. These systems are uncovering entirely new cosmic behaviors and elucidating the physics of short timescale events, an area previously beyond our reach. One of the most exciting frontiers is multi-messenger astronomy, which combines information from light, gravitational waves, and ghostly subatomic particles called neutrinos. In April 2019, ZTF's automated system flagged a new transient event. Astronomers quickly identified it as a tidal disruption event, or TDE, the cataclysmic shredding of a star that wandered too close to a supermassive black hole. 6 months later, the IceCube Neutrino Observatory, buried in the ice at the South Pole, detected a single, extremely high-energy neutrino that appeared to come from the same spot in the sky. Because the ZTF detection was automatically logged and classified by a broker, astronomers could quickly connect the two events. This discovery provided some of the first strong evidence linking a TDE to the production of high-energy neutrinos, a major advancement. The constant monitoring of the sky has also led to the discovery of entirely new classes of cosmic explosions. Among the most puzzling are luminous fast blue optical transients, or ELF-bots. These events are far brighter than a typical supernova, but fade away in a matter of days instead of months. The first well-studied example, at 2018 Cow, nicknamed the Cow, baffled astronomers with its combination of extreme brightness and rapid evolution. More recently, ZTF discovered an even stranger object, named at 2022 TSD, or the Tasmanian Devil. This LF-bot produced a series of at least 14 powerful, repeating flares for months after its initial explosion, repeatedly reviving itself like a zombie. This behavior defies all existing models of how stars die. These systems are also critical tools in the hunt for the optical counterparts to gravitational waves. When two neutron stars merge, they send ripples through the fabric of spacetime that can be detected by observatories like LIGO. This collision is also expected to produce a faint, rapidly fading glow called a kilonova. The challenge is that the gravitational wave detection provides only a rough location on the sky, a search area that can be thousands of times the size of the full moon. Wide-field telescopes like ZTF must rapidly scan this entire region, and their automated alert and broker systems are essential for sifting through thousands of unrelated variable stars and asteroids to find the one faint, fading object that marks the site of the cosmic collision. The data streams from modern surveys are too vast for professional astronomers to handle alone. But this data deluge has also opened the door for citizen science on an unprecedented scale. Professional researchers are linked with millions of volunteers worldwide through platforms like Zooniverse, an official partner of the Rubin Observatory. A recent success story was the Active Asteroids project. Researchers were searching for a rare type of object in our solar system, asteroids that occasionally sprout comet-like tails of dust and gas. These active asteroids are thought to hold clues about the distribution of water in the early solar system, but they are exceptionally difficult to find. The project team turned to the public for help. They uploaded hundreds of thousands of images from the Dark Energy Camera Archive to the Zooniverse platform and asked volunteers to look for anything that appeared fuzzy or had a tail. The response was overwhelming. More than 8,000 volunteers joined the search. Their effort led to the identification of 16 previously unknown active asteroids. AI, too, is revolutionizing astronomy. New algorithms are going beyond classification to predictive modeling. AI is also being used to create highly realistic simulated images of the cosmos. These galactic forgeries help astronomers test their complex theories of the universe and prepare the massive data processing software needed for future surveys. A long history of discovery in astronomy has been driven by serendipity, by an observer being in the right place at the right time to notice something completely unexpected. A key objective for the next decade is to build AI systems that can automate this process of serendipity. The goal is to create algorithms that can flag any object that does not fit into a known category, bringing the truly weird and novel to the attention of human experts. In the coming years, an AI on a broker could automatically identify a high-priority candidate, like a potential kilonova, and automatically task a network of robotic telescopes around the world to observe it. Another AI could analyze the resulting data, and a complete report could land in an inbox, all within minutes of the initial discovery. This would create a global robotic nervous system for astronomy, capable of observing and reacting to celestial events with superhuman speed.